So hello, last time we looked at a puzzle about liking shapes and colors and not being picky about what you like. I like triangles or maybe circles, and I like blue things or maybe yellow things. And I am happy with something if it has my favorite shape or my favorite color. So suppose I like triangles. What can you say about the rest? A lot of people would say here, oh yeah, that means that you don't like the yellow circle because you like the blue triangle. But you see here, I may like the blue triangle for several reasons. I may just like triangles so much that I don't care that it's blue, although I would rather have the yellow one. Or I may like blue things so much that I don't mind it being a triangle, even though I would prefer a circle. Or indeed, it could be that I like blue things and I like triangles, so I'm really happy about having the blue triangle. So think about it maybe this way. Suppose I like to wear jeans or I like to wear blue pants. And if you see me wearing blue jeans, then, well, okay, you may infer that I wouldn't wear yellow pants. But suppose you see me wearing black jeans. Does it mean that black is my favorite color? Well, maybe not. Or you see me wearing some kind of blue pants. Does it mean that I like wearing pants? Well, no, I'd rather have jeans, but, you know, at least it's blue. So in this example, if I like the blue triangle, there is really not enough information for you to say if there is any of those figures that I wouldn't like. You know that it exists, but you really don't know which one. It could be any of the remaining three. So let's talk more about the probably most complicated because of the connotations in English of the logic connectives. By the way, people who do circuitry, who do logic circuits, they get rid of if-then as soon as they can, and they just deal with comfortable and, or, and not. And we will do it at times too, just to make things easier. But because human beings tend to say a lot of things, if something, then something, let's just look at different ways of saying it and different statements with if-then that sometimes mean the same thing, sometimes don't. So just to remind you, a while back we saw this puzzle, and this was our introduction into the if-then construction. You were trying to figure out which cards you need to turn to check that the following holds. If a card has a J on one side, then it has a 5 on the other side. So before we go on, let's talk about something really complicated. Let's talk about English. And math is easy. English is hard. Here is an example why English is hard. Here are all the different ways, well, maybe not all, but at least some of the different ways to say A implies B in English. And some of them kind of make sense. Some of them, at least for me, takes a while to wrap my head around. So the one that we mostly use so far is if A, then B. You could also skip the word then and just say if A, comma, B. For example, if A is it's wet and B it's slippery, then you could say if it's wet, it's slippery. Well, yeah, kind of makes sense. If you want to be more formal, you could say A implies B. This is how we read that arrow, the implication. And this is how you would typeset this arrow, by the way, if you are using some of the software packages. You could say, it's wet implies that it's slippery. If it's wet, it must be slippery. But here is the one that really takes a while to wrap your head around. It's wet only if it's slippery. Now, am I saying the same thing as if it's wet, then it's slippery? The non-obvious answer is yes, and hopefully after we talked about several equivalent statements to A implies B, You could kind of see why this is the same, but for an English speaker, that's really not obvious. For a non-English speaker, even more so. So here's another example of saying if it's wet, then slippery. It's slippery unless it's not wet. So now, somehow in English, we needed to change the order, and with the word unless, we even needed to put the not in front of A. Well, that's probably the strangest one, at least that's the only one which is in common use where you actually have to put a not in it. Others, you change the order, maybe, but then still, if you have something under the if part, if it's without only, then it would be A, and the other part would be the B. For example, it's slippery when it's wet, or if it's wet, or whenever it's wet. If you want to be even more formal, one analog of A implies B would be B follows from A. Being slippery follows from being wet. If I slip, that follows from somebody spilling the water or coming in from the outside with the snow on their boots. And in math books, you would sometimes see expressions sufficient and necessary. It's sufficient for A to be true to make B true. If it's wet, it's sufficient to make it slippery, no matter why it's wet. Note that here it can be slippery for another reason. Maybe somebody didn't spill water. Maybe somebody spilled olive oil on the floor. Then it wouldn't quite be wet, but it still would be really slippery. And another part, the kind of the other direction to sufficient is necessary. It's necessary to have B true in order for A to be true as well. It's necessarily slippery when it's wet. You cannot have wet without it being slippery. So when you are trying to translate English into logic and logic into English, which I would say is by far the hardest part in this course, translating between English and logic, keep in mind all of those really different and different sounding ways of saying the same thing, the same logical thing. A implies B. Something that's so clear and well defined and with a short truth table has all of those complicated ways of talking about it. So now let's look at not maybe quite the same way of saying A implies B, but equivalent way. So say A implies B is something like if a card has a J on one side, then it has 5 on the other. Another statement which has the same truth table, an equivalent statement, is its contrapositive, which is not B implies not A. And the way we get it is we switch the order of A and B and we negate both of them. So we get if the card does not have 5 on one side, then it cannot have J on the other. If a card has a J, then it must have a 5. So if it doesn't have a 5, then it cannot have the J. And you could kind of see that this is an equivalent statement. There is an easy proof of it, because if you use the way to represent implication with ors and nots, not something, something implies something is not the first thing or second, you could get that both of them open up into not A or B. Well, you could switch the order around as we just talked about. So those two things are equivalent. We didn't really need to do a truth table. And here is something that you write as a different formula, but it has the same value. So why would you want to do this? Well, first of all, maybe you want to simplify not B implies not A into A implies B, because there are fewer symbols to write. But often it makes sense also from the point of view of understanding the problem. For example, when you say if a card has a J on one side, then it has 5 on the other, it kind of tells you that you have to look at every card on which you see a J to see a 5. But remember, we also needed to look at every card that doesn't have a 5 to check that there is no J on the other side. And what tells you why you would need to do it is the fact that it's a contrapositive. Okay, so let's now look at two other ways of writing A's and B's and the arrow between them and negation in various parts. So B implies A if you just reverse the direction of the arrow but you don't put negation in it, is the converse of the original implication. And if contrapositive had exactly the same truth table as the original implication, the converse doesn't. Because if you have A being true and B being false, then A implies B is false. However, B implies A is true. If you have a card with a J on one side and 2 on the other, it will make, if it has a J, then it has a 5 false. But it would do nothing to, if it has a 5, then it must have a J. So another common mistake is to think that because you switch the order, then you negated something. An easy way to see that negation of an implication actually cannot be something, arrow something, no matter what those things are, is to look at the number of satisfying and falsifying assignments. When you have something implies something, it will be true in 3 possible scenarios and false in 1. However, if you take its negation, so you flip every true to false and every false to true, you end up with a situation when there is 1 scenario when it's true and 3 scenarios where it's false. So you cannot really do it with something arrow something. And another way to check it is to find an explicit scenario where A implies B, negation of A implies B, would have a different value that B implies A. One such scenario is when A is true and B is true. Then B implies A is true. If something has a 5 on one, if a card has 5 on one side, has J on the other, well, if you have a card with J and 5, that's fine. But not A implies B will be false in this case. Exactly because A implies B was true. And let me throw in yet another word in it, which is the inverse. That one you probably see less often than converse and contrapositive. And the inverse is the contrapositive of the converse. So if you have B implies A and you take a contrapositive, you will end up with not A implies not B. So in our card example, it would be if the card does not have a J on one side, it cannot have 5 on the other. It's equivalent to converse, but it's very different from your original implication for exactly the same reason as before. So let's look at a few examples of contrapositive versus the converse, because this is one skill that you, after taking this course and being skilled with logic, will have that I wish more people had in reality. Suppose you hear a sentence. If a person is carrying a weapon, then the airport metal detector will ring. It's exactly the same truth value as if the airport metal detector does not ring, then the person is not carrying a weapon. Because if the airport metal detector does not ring, then the person is not carrying a weapon is a contrapositive to our original sentence. It's definitely not the same as if the airport metal detector rings, then the person is carrying a weapon. You know, maybe they just left some coins in their pocket or a key somewhere. And it absolutely doesn't contradict the description of the metal detector that the airport bought, which says, if a person is carrying the weapon, then the metal detector will ring. It says something kind of orthogonal. If the metal detector rings and the person's carrying a weapon? Well, maybe they do, maybe they don't. We really cannot figure that out from the original statement. Here's another very common example. So suppose somebody has a bad cold and they want to figure out if they have a flu. And they go and they take this test, and they hear, if you're sick, then the test will come out positive. Well, okay, that's good. If you're sick, then it will come out positive. But what if you want to know that you're not sick? This doesn't really tell you what happens if you're not sick. You could be healthy and the test still would come out positive. The sentence, if the person thinks that the test is positive, really doesn't tell you much. And in fact, this would be true even if you have a kind of useless test which is always positive and never tells you anything else. Or here is another example that, again, you could think of people who would reverse the sentence and get something strange in real life. If he is a murderer, then his fingerprints are on the knife. Well, okay, fine, that's true. But suppose they go and they find somebody's fingerprints on the knife. Would it be logically correct to conclude that those fingerprints belong to the murderer? Well, think about it. Who knows, maybe the murderer took the knife from the kitchen and the chef's fingerprints are on the knife. That doesn't make the chef a murderer. That may make chef a victim, if anything. So even though if he is a murderer, his fingerprints are on the knife, would be logically correct, inferring from this that the fingerprints that you found on the knife belong to the murderer is really not logical. So let's just look at this table to summarize all those different ways to take A implies B and turn the arrow around and put negations on stuff. So if you have A implies B, the implication, then its contrapositive, an equivalent statement, is not B implies not A. If he is a murderer, then his fingerprints are on the knife. If his fingerprints are not on the knife, then he's not a murderer. He can go free. That's perfectly logical. Now, a different statement would be the converse. If he's a murderer, his fingerprints is on the knife. His fingerprints are on the knife, he's a murderer. Well, that really doesn't follow. That's not the same thing. That's something completely different. And finally, the last one, the inverse. If he is not a murderer, his fingerprints are not on the knife. Well, that's the same as saying if his fingerprints are on the knife, then he's not. Then he's murderer. So the converse and inverse are equivalent to each other, just like the original statement and contrapositive are equivalent, but it's not really the same, or in many cases even related statement, the original implication and its converse. They have different truth values. So finally, let me talk about the combination of the two. So far, I was just saying that they're different, but there is one more connective, the one that you've seen before in the knight and knaves puzzles, that combines the two. And this is a if and only if connective. A is true if and only if B is true. In mathematics, sometimes you see people shorten if and only if to if with 2f. That's not a typo, that just means that the arrow goes both ways. And if and only if is true whenever both A implies B and its converse B implies A are true. For example, suppose when we are teaching this course on campus, we have two sections, and we have a Wednesday section and a Monday section. And the section 2 has a lab on Monday, and the section 1 has a lab on Wednesday. I may say, come to the lab on Monday if and only if you are in the section 2 of 1002. That means if you are in section 1, don't come on Monday, we don't have enough space, your time is on Wednesday. But if you are in section 2, please come on Monday rather than Wednesday, because this is when your time is here. Equivalently, you would say, if you're not in section 2, don't come on Monday lab, come on Wednesday lab. And also, if you are in section 2, please do come on Monday. And just to remind you, we use that be conditional a lot when we talked about knight and knaves, because somebody is a knight if and only if what that person said is true. Arnold is a knave if and only if what he said is true. Arnold would never be able to say, I'm a knave. So let's look at yet another puzzle. So the puzzle goes like this. Imagine that you discover a note signed by a pirate who loves logical puzzle. And he says that he has hidden a treasure somewhere in his house, somewhere on the remote island. And then he listed 5 true statements and say that the treasure belongs to whoever can figure out its location by solving the puzzle and saying the treasure is here. Here are the statements. If this house is next to the lake, then the treasure is not in the kitchen. Okay, fine. If the tree in the front yard is elm, then the treasure is in the kitchen. Okay, there is still a tree in the front yard. Good. And also you look around and say, this house is next to the lake, just like it said. Great. Another sentence is, the tree in the front yard is an elm, or the treasure is buried under the flagpole. And if the tree in the backyard is an oak, then the treasure is in the garage. Now, the question for you, where is the gold? Can you find the treasure? Can you infer the location of the treasure by just taking those 5 statements that we assume is true and getting an answer? Is it true that the treasure is buried under the flagpole? Is it in the kitchen? Is it in the garage? Can you show that one of those is true by just looking at those 5 sentences? This is something for you to think for next time.